So welcome to the session 4 of 6th unit, the processors and pipelining. So in today's session, we're going to learn about the superscalar processor and the VLIW architecture. So in scalar processor, what happens is the scalar processor will work with a scalar quantity. So that is, it can perform a single arithmetic operations like 2 plus 3. So where 2 plus 2 and 3 are the scalar quantities. So in scalar processor, in one clock cycle, it executes one instruction. And to execute that one instructions, it uses one pipeline. So here we having a advanced version of a scalar processor, and we call it as a superscalar processor. Superscalar processor is an advanced version of scalar processor, or it is the faster version of scalar processor. So where the multiple instructions can be executed at a time. That is, in one clock cycle, it can execute multiple instructions. So we can define a superscalar processor as a single processor in which many instructions are executed concurrently is known as a superscalar processor. So that is, in one clock cycle, it can execute multiple instructions. And to execute multiple instructions in one clock cycle, it can make use of multiple pipelines. So these processors exploit more instruction level parallelism in user program. So that is, it follows instruction level parallelism. That is, it can execute multiple instructions in parallel. The instructions which are executed in parallel, that may be of type the load or store or any arithmetic operation instructions. The limitation of instruction issue degree M is given as. So as I told that in superscalar processor, in one clock cycle, it can execute multiple instructions. Then how many instructions that it can execute? So that it ranges from 2 to 5. So we call that M as an instruction issue degree. So in one clock cycle, so we can execute 2 to 5 instructions in parallel. So if we want to fully utilize a superscalar processor of degree M, then M instruction must be executed in parallel. So that is, if you want to make a full utilization of a scalar processor, the how many instructions we are going to combine, all that instructions should be executed in parallel. So we are going to group instructions or the multiple instructions that are going to execute in parallel such that there should not be dependency between the instructions. So that is, there should not be any data dependency or there should not be any resource dependency. A superscalar requires a high degree of instruction level parallelism in programs so that it depends more on optimizing compiler to exploit parallelism. So that is, as I told that in order to execute multiple instructions in a single clock cycle, there should be no dependency between the instructions. If there is any unnecessary dependency between the instructions, and that should be eliminated using additional registers. And in order to handle that dependency, so it can use the compiler based optimization and any hardware technique. So here we having an example of superscalar processor. So before going to study the superscalar processor, what happens in scalar processor? So here we having 4 instructions, I1, I2, I3, I4. So each instruction has been divided into or consists of different stages. So here we having 4 stages: the fetch, decode, execute and write. So in scalar processor, what happens in one clock cycle, one instructions can be executed. So now there are 4 instructions here. Each instruction is having 4 phases: fetch, decode, execute and write. So here in first clock cycle, it starts the execution of first instruction that it will going to perform a fetch phase. Once the fetch phase has been done, it will go for the decode phase. So when the first instruction go for the decode phase, we can start executing the second instruction. That is, the second instruction will going to perform the fetch phase. When the second instruction is performing a fetch phase, the first instruction is in decode phase. after the completion of a fetch phase of instruction 2, it can go for the decode phase. When it go for the decode phase, so we can start executing instruction 3. That is, the instruction 3 can perform the fetch phase. So during the clock cycle, during the third clock cycle, the instruction 3 is in fetch phase, whereas the instruction 2 is in decode phase, and whereas the instruction 1 is in execute phase. So like that, the instructions can be executed using the pipelines. So now, in order to execute these 4 instructions, the Scalar processor will going to take 7 clock cycles. So if there are 9 instructions, it takes 12 clock cycles for the execution. So now let's study how the superscalar processor works. So as I told that in superscalar processor, in one clock cycle, the multiple instructions can be executed, and to execute that multiple instructions, it can make use of multiple pipelines. And that instruction issue degree that will be defined with M. So here in this example, we have taken M equal to 3. It means that in one clock cycle, it can execute 3 instructions. And to execute 3 instructions, it uses 3 pipelines. And each instruction has having 4 phases: fetch, decode, execute, and write. So during the first clock cycle, the execution of 3 instruction will begin. So it will going to perform the fetch operation. Once the fetch operation has been completed, it will go for the decode phase. So whenever the first 3 instruction go for the decode phase, we can start executing the next 3 set of instructions execution. So that is, the instruction 4, 5, 6 can be get executed, and that will be in fetch phase. When the instruction 4, 5, 6 is in fetch phase, the instruction 1, 2, 3 will be in decode phase. So here in the second set, once the fetch phase has been done, that will go for the decode phase. So when it enters into the decode phase, we can start executing the another set of instruction. So that is, we can start execution of the instruction 7, 8, and 9. So the 7, 8, 9 will be in fetch phase. By the same time, the instruction 4, 5, 6 will be in decode stage, and instruction 1, 2, 3 will be in execute phase. So like that, the superscalar processor can execute the instruction in a shorter clock cycle compared to the scalar processor. So here, in order to execute the 9 instruction, it takes around 6 clock cycles. So whereas in a case of scalar processor, in order to execute 9 instructions, it takes 12 clock cycles. So this is a simple architecture of a superscalar processor, which contains a fetch unit, the decode or dispatch unit, and a executional unit. The fetch unit will going to fetch the instruction. So once it fetch the instruction, it will send those instructions, it will decode that instruction, and it will send that instruction to the processor for the execution, which contains multiple executional units in order to perform the pipeline and parallelisms. The advantage of the superscalar processor is a speed access. So that is, if there is no dependency between the instructions, so we can execute multiple instructions in a single clock time, so that the throughput can be increased. But the limitation of a superscalar processor is the dependency. If there is a dependency, in order to handle that one, so we are going to make use of a compiler, or compiler optimization is required. So next concept is a VLIW architecture. As I told that in a superscalar processor, what happens? It executes multiple instructions in one clock cycle if there is no dependency between the instructions. If there is a dependency, that should be handled by the compiler. So as a advanced feature of the superscalar processor, we having a VLIW architecture. So VLIW stands for a very long instruction word. So it is a technique that combines multiple standard instructions into one long instruction word. So that is, it will going to combine the multiple standard instruction, and that combination of multiple standard instructions is called as a one long instruction word. VLIW processor rely on the compiler to exploit the instruction level parallelism for determining the instructions which may be executed in parallel. So how the VLIW processor works? As I told that, so it will going to combine the multiple standard instructions for the execution. The processor is there to perform that execution. But before giving the instruction to the processor, we will be having a compiler. Then what this compiler will do? So it will going to choose the operations that can be performed together so that there will be no dependency in between them. So that is, so here we having a group, the compiler will going to form a group which contains multiple standard instruction where there will be no dependency between those instructions, and that group is given to the processor for the execution. In the same way, the compiler will going to perform another group, or it will going to create another group which is a combination of multiple standard instructions where there will be no dependency, and that group is given for the processor for the execution. So this the operation which are grouped here, or the instructions which are grouped here, we call it as a word, or we call it as a very long instruction word, that is VLIW, as a combination of multiple standard instruction with no dependency. We call it as a very long instruction word. So as I told that these groups are given to the processor. So it depends on, or on what basis we can form this group. It depends on how many functional units are provided in the processor. Suppose for example, the processor is provided with two functional units for load operation and store operation, and one functional unit provided for additional operation and one for the multiplication operation. Then this compiler has to group such kind of instructions such that there should not be dependency between the instructions. So now let's study an example of the VLIW architecture. That is how an instruction is executed in VLIW processor. So here we having an instruction which performs AX plus BY plus CZ. In order to execute this, we can form a group of instruction where there will be no dependency between the instructions. So here we are going to make use of the load operation, store operation, addition operation and multiplication operations. So what or how it will going to execute it? So first it need to load the operand A and operand X. Then it need to load the operand B and operand Y. Then it need to load the operand C and Z. Then it need to perform the multiplications like AX, BY and CZ. Then it need to perform the multiplication. In a Scalar processor, in order to execute this instruction, it takes almost 11 clock cycles. Then how we can reduce that? By using the VLIW architecture. So in VLIW architecture, we're going to form a group. So here in the first group, so we're going to perform load A and load X, which we're going to load these two variables. So there is no dependency between the instructions. In a second group, we're going to load B and load Y. So at the same time, we can perform the multiplication of these two operands. So that is mul A and X, which will going to perform the multiplication of A and X, and the result of this will be stored in X. So again, in the second group, we have used three instructions where there will be no dependency between the instructions. Then in a third group, we're going to perform load C and load Z. By the same time, we can perform multiplication of B and Y. So as a result of this multiplication of B and Y, the result will be stored in Y. So now at the end of third stage, or by the end of this instruction, so we having the result of multiplication of AX, result is stored in X, multiplication of B and Y, result is stored in Y, and we have loaded C and Z. So now in the next group, so we're going to multiply C and Z. By the same time, we can perform the addition of these two, that is ax and by. That can be done by add x comma y. The result of this will be stored in y. So now at the end of this instruction, so we having the result of multiplication of cz and the addition of ax plus by. So now we going to perform the last instruction, that is add y comma z. So which we're going to perform the addition of ax plus by with cz. So in order to execute this instruction, or in order to execute this equation, the number of clock cycles required is 5. That is, in 5 clock cycle it can be executed in VLIW processor. The advantages of VLIW: it is a simple hardware, and the power consumption can be reduced in VLIW processors. Compiler can detect the parallelism based on the global analysis of the whole program, and the simpler instruction issue logic is provided here. Then the instructions being implemented with the shorter clock cycles than the superscalar processes. The disadvantage of the VLIW architecture is the compatibility across the implementation is a major problem in VLIW, and the code density is the another problem. The applications of VLIW. The VLIW architecture is suitable for DSP, that is the digital signature processing applications. The another application is the processing of media data, like the compressions or the decompressions of images and data speech. So this is a simple architecture of VLIW. So we will be having a fetch unit which will going to fetch the instructions. As I told that it will going to combine the multiple standard instruction, and it will form a very long instruction word, that is a single multi-operation instruction that will be given to the processor for the execution, where the processor contains the multiple execution units. So this is all about today's session. So we having some multiple choice questions here. That the first question is, the VLIW stands for option A, very long instruction word, option B, very long instruction width, option C, very large instruction word, option D, very long instruction width. So VLIW stands for very long instruction word, that is option A. The second question, the important feature of the VLIW is the option A, ILP, that is instruction level parallelism, option B, cost effectiveness, option C, performance, and option D, none of the mentioned. So here the answer is the instruction level parallelism, that is option E. The next question, the parallel execution of operations in VLIW is done according to the schedule determined by option A, the task scheduler, option B, the interpreter, option C, the compiler, and option D, encoder. So here the answer is C, that is compiler. The next question, the dash plays a very vital role in case of superscalar processes. Option A, compilers, option B, motherboard, option C, memory, and option D, peripherals. So the compiler plays a very vital role in the case of superscalar processors. So answer is option A. The next question, the limitation of instruction issue degree M is given by option A 2 to 5, option B 2 to 105, option C 20 to 50, and option D 5 to 15. So answer is A, that is 2 to 5, as I explained. So in one clock cycle in superscalar processor, it can execute multiple instructions. So in one clock cycles maximum it can execute 5 instructions, so that it ranges from 2 to 5. Option A, that is 2 less than M less than 5, which indicates the M ranges from 2 to 5. So this is the end of session 4 on processors and pipelining. So these are the textbook referred to create the contents. Thank you to all the members of a team. So if you're having any suggestions, please write your suggestions to this link. So thank you all.